Start now, right? I forgot my watch, so I'm probably late. But sorry. Am I good? Okay. Let's begin. You hit record? Okay. Dear Father, we thank you for this day, and we thank you for the quietness of this room. Help us to enjoy the quietness. Help us to learn what a vector space is and a subspace, and I just pray that these ideas would be cemented in the students' minds as we go over this material. Lord, in your name I pray. Amen. Okay, so I have to start with a definition. So this course is taking it takes a rather drastic turn at this point, and we start with this definition. Now, so the definition is, what is a vector space? So before I give you the formal definition, let me just try to tell you kind of heuristically in words what it is. A vector space is some set, all right? Some set of objects. The elements in the set, we call them vectors, all right? What makes it a vector space is that there's a couple things you can do. First of all, second, the vector space it's a vector space with respect to some choice of field, all right? So one of the things you can do with these vectors is you can take scalar multiples of any vector, and if you take a scalar multiple, multiplying by something in the field, you get back to the vector space again. The other thing you can do is add. So here's what we typically say. A vector space V over a field F is a set with two operations, and I'll use some notation. One will be totally unsurprising. Plus is a mapping from the Cartesian product of the vector space with itself back to the vector space again. So that's called vector addition. And the other one, let me use a dot for, not to be confused with the dot product. The dot operation goes from the field across the vector space back to the vector space again. So typically, I mean, there's not much to say here. I mean, plus, what does it do? Plus has x comma y mapping to x plus y, all right? Whereas the scalar multiplication has something like alpha comma x mapping to what we'll denote as alpha dot x. Now I'm doing alpha dot x as a temporary notation. Typically speaking, for the scalar multiplication, we allow ourselves to do this. We just denote scalar multiplication by juxtaposition, side by side. And in fact, honestly, in applications, often we even allow ourselves to put the alpha on the other side, although strictly speaking, that's not in the definition. All right, so then we have a system of axioms. Axiom 1, axiom 2, axiom 3, axiom 4, and I'll write them out here. Axiom 1 is that x plus y is equal to y plus x for all x and y in the vector space. Axiom 2 is that x plus y plus z is unambiguous. In other words, so the first thing is what? It has a name, right? What's the first thing's name? I'll put the name over here. So this is commutativity of addition, right? This right here is the associative property of addition. What else is there? Well, axiom 3. There exists a zero vector, 0, in V, such that x plus 0 is equal to 0 plus x is equal to x for all x in V. Okay, then axiom 4 is that for each x in V, there exists minus x in V, such that what? Such that x plus minus x is equal to our friend from axiom 3, 0. All All right, so the axiom 3 was existence of additive identity. Axiom 4 was addition closed under inverses, additive inverse, right? I'm resisting the obligatory comment. All right. It's not easy, but I did it. The first 4 here, if you just take these in isolation, already is a thing. Well, there's a little bit more. The first 4, and actually what I'll call axiom, let me just throw in axiom 10 right now. Axiom 10 is that, axiom 9 is that x plus y is a single element in V. In other words, axiom 9 is really saying that if I cross out operations and I write function there, addition is actually a function. It's a single valued assignment of a vector for each pair of vectors. So these things taken together, well, the axioms 2, 3, 4, and 9 taken together say that a vector space is a additive group because it's associative and it's got an additive identity and there's an inverse for everything. It's an additive group. Axiom 1 thrown on the heap makes this actually a commutative abelian group. Oh, sorry, maybe redundant. Let's see here. It's an abelian group. That's what this gets you. V is an abelian group with respect to addition. But there's more. All right, there's more. So axioms 5, 6, and so forth. Axiom 5 is that 1 times x is equal to x, all right, for all x in V. Axiom 6 is that if we have A times B, I guess I should put a dot in here. Oh, I'm sorry, no dot. Excuse me. So this is the multiplication in the field. A multiplied by B times x is equal to A scalar multiplied times B scalar multiplied times x. And that's for all A and B in the field and x in the vector space. Sorry, I was going to give you guys a handout with these, and so I didn't have to write this all out. But then I had this thing called a math meeting. You know the thing about math meetings? The really annoying thing about math meetings? The worst part about math meetings? We don't talk about math. See here, A times x plus A times y, which is offensive to me. All right, let's see here. So this is for all x and y in the vector space and A in the field. Let's see here, axiom 8. So A plus B dotted scalar multiplied by x is equal to the scalar multiple of x by A plus the scalar multiple of x by B. And that is for all x in V and for all A and B in F. One more axiom to go, and then I'll stop with this axiom business. Axiom 10 is that C times x is a single vector, single element in V for each C in the field and x in the vector space. All right. So, I mean, if you just kind of take a step back and look at this, what we're really saying is that scalar multiplication and in vector addition works just like what? What satisfies this structure you already know about? What example? Real numbers. Very good. So what are examples of vector spaces? So let's start making ourselves a list of examples. I like that one. V equals to the real numbers. Now, what's your choice of field? See, it's ambiguous until you tell me what the choice of field is. Vector space over what? You will not choose C. We could take the field. So the most natural choice, of course, is just the real number system itself. It's kind of a boring vector space, but that is a vector space in which the vectors are also scalars. It's kind of a quirky example. Of course, I can take that example and I can go a couple different ways with it. I could give you a second example, which would be the vector space V equals to the reals, and I could take the field to be, I could take it to be other things. For example, I could take it to be the rationals. Is the scalar multiple, I mean, if you check it, these axioms are still satisfied if you take the scalar multiples, the scalars from the field of rational numbers. Still a vector space. But in this vector space, scalar multiplication is done only by rational numbers. And 1 and 2 are very, very different examples. We will learn the meaning of this word called dimension as we go on in here. Once we know what that word means, we can say that example 1 is a one-dimensional vector space, whereas example 2 is an infinite dimensional vector space. But I can go a different direction with these examples. Example 3, I could take this. How about just V is equal to a field? And just take the scalars the same, you know. Sorry, it's hard to see the idea here. But just any field is a vector space if you take the scalars from the same field. So like Z mod 3, Z mod 5, Z mod 11 vector spaces, right? Can we be greedier? What other class of examples do we have that we've already worked with? How about this? How about if I look at m by n vectors, rather look at V equals to m by n matrices, right? How about m by n matrices over a field? Could be real, could be complex, could be over Z mod 3, whatever. Pick your favorite field, take the m by n matrices. Is the sum of n by n matrices, again, an m by n matrix? Yes, so we got axiom 9. Is it a single m by n matrix? Absolutely. How about the scalar multiple? So my old quote-unquote scalar multiple matches my new abstraction of the notion of scalar multiple, right? So yes, in fact, this is also a vector space over what? Over the field, right? And again, you could do weirder stuff. Like I could look at real 2 by 2 matrices over the rational numbers as a vector space if I wanted to, but that'd be kind of a weird example. So that's what I'm writing right here. So 1, 3, and 4, these are the usual meanings. Okay, these are sort of, let's say, these are standard interpretation. Standard interpretations of our f and fm by n. So, you know, a given point set, right, could have different scalars, but unless we say otherwise, it's understood that if I'm looking at, like, for example here, let me just expand on 4. For example, if I take v equals to Rn, the standard choice of scalar here is what? If I forget to say otherwise, you should assume the field is what? The reals, right? That's the customary thing to choose there. Now, if you're ever in doubt about that, or if you think the question's about that, you're free to ask me, right? One of you already asked me about the homework because I asked about what's a subspace in this homework that I assigned you guys. And that begs the question, what are the scalars, right? All right, let's continue with this cavalcade of examples. What else we got? What else we got? N by N matrices, real numbers. Anything else? How about this? How about if I let what if I let v equal, say, functions? All right, set of functions, and here I'm just talking about functions from, let's say, a set into the real numbers, just to get started. Is this a vector space? I guess I usually would use the notation, not just f. I would usually I use the notation. This is notation I use for this. I'll use like functions, functions from S to R. So that's my like standard notation for functions that take S as the domain and R as their codomain. Just functions. There's no extra structure assumed here, just that they're functions. Okay. So what would the vector space structure you could give to V be? How would you, if I give you two functions, say f and g are elements of V, then how to define f plus g is defined as how? How do you define the sum of two functions? I'm asking you to go back to a simpler time. This should be nostalgic for you. It should take you back to high school or something, right? Or maybe you're happy to be past that time. I don't know. So we define it pointwise, right? Addition of functions is defined pointwise. So what I do is f plus g, I take a point, say x, and what's the new functions defined? What is it? F of x plus g of x. Is this a single valued assignment for each x for this new thing called f plus g? Absolutely, because f of x is a single thing, g of x is a single thing, so of course the sum of single things is a single real number. So a pointwise definition of a function makes sense, and this of course is for all x in where? In S. Now S, what I just said S is a set, so what is the set? Doesn't matter. It could be a set of 3 cats. It could be the grades you guys got in quiz 1. It could be, I don't know, whatever you like. It could be lots and lots of different things, you know? Oh, I'm sorry, is that still, it's too soon? It's too soon for that, yes, sorry. So that's the definition of tradition. Now, again, by default, what would our choice of scalars be? So like custom, if you're not weird and trying to be malevolent to the students, I would usually say this is over the real numbers. But certainly, it would also be a vector space over any subfield of the real numbers as well. But I would personally view that as a non-standard vector space structure. Okay, so scalar multiplication, we also have to define what's c times f of x. I think you guys can tell me what it is. What is it? It's just c times f of x, where this is real number multiplication. And so there you go. We can define the sum or the scalar multiple of any two functions from S into the reals as, again, a function from S into the reals. And you can run through it. Does it satisfy these axioms? Is it commutative? Is the addition commutative? Yes, the addition is commutative. Why? Because real number addition is commutative. Is the addition associative? Yes, because it is, right? It is inherited from the associativity of the real number addition. Is there something called the zero function? Now, there's something we should think about a little bit. Is there something called a zero function? How would you define it? 0 of x is equal to what for all x? 0. So it defines 0 in V. So this 0 is sorry, 0 is very degenerate. It has many meanings. There's I'm using it both as a function and as a real number. I hope you can forgive me. It's what?
It's everything.
It's everything, yeah. And of course, if you want to get minus the function, you just do what? You multiply by -1, right? Yeah.
So if you were trying to prove that something is like some field in a certain vector space, would you have to show that would you have to go through and prove all
Some
n
field is a vector space?
Not a field, I don't know.
Oh, just some set.
Yeah, some set.
Yeah.
Would you have to then go through and prove like individually each of these?
Technically, yes. You would have to go and check, 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 check. Now, for those of you who are logical purists, there is some refinement of this, which is a reduced set of axioms. Maybe, I forget, maybe you can cut it down to 8 or 6. I forget exactly. But for pedagogical reasons, we present it this way. It is a little bit redundant. It's especially redundant that I have written up here this, and then also included axioms 9 and 10. Those are the same meaning. But yeah, short of some other structure, I'd have to go back and go check through axioms. Now, I'm not going to write that out because you guys don't want to see it, and I don't want to write it. But we can all agree, as you just think through these examples, that it's clear that those things are right. Right. So I'm trying to create for us a list of standard examples we can use. All right? Can you take 6? We can take 6 and we can bump it up a notch. Check this out. If I take V to equal the functions from any set into a vector space W, vector space over a field over F. If you did this, you can easily, by almost the same argument as 6, prove that that is a vector space over F, where we're, again, where the addition is the addition of functions, right? So like, for example, I would take F plus G of X is equal to F of X plus G of X again. Now, how do I know that F of X plus G of X is again an element of W, right? If F and G are functions from S to W, right? How do I know that F of X plus G of X is again something in W? What did I say about W? It's a vector space. So, yes, F of X plus G of X is in W. And how about the scalar multiple? If I take C in the field F, well, that's C F of X, right? And again, if W is a vector space over the field F, then certainly C times F of X is again something in the field F for arbitrary X. And there you have it. At least those operations are well defined. And again, you can go through this laundry list of axioms and see that it works. So there's nothing really especially special about the real numbers up here, right? It just so happens that those are a vector space, and that's why this works. You guys have any examples to add to my list? How about this? And this, in some sense, is a specialization of 6, but it's an important one. We can take V to be, let's say, things of the form ax squared plus bx plus c, such that a, b, c are real numbers. Oftentimes, I call this like p sub 2r, in other words, for possibly degenerate quadratic polynomials with real coefficients. What's a mouthful? Blah, 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 blah. Yeah. How would you define addition? How do you define addition and scalar multiplication of polynomials? Just like you already know. So in other words, if I have, I don't even want to write it down really, but I'll do it. All right. B1x plus, how do you add these? Right? What's the scalar multiple of a polynomial? Multiply the coefficients like you've been taught, right? In some sense, this is really a special case of 6, right? Taking S to be the reals and thinking of functions as polynomials. Now, but let me show you something weirder. Well, let me just bump that up a notch. So if we take V, we use this notation, R parentheses X, So what this means is polynomials. This is polynomials in X with real coefficients. So this is basically the set of, like a0 plus a1x plus da-da-da plus anx to the n, such that a0, da-da-da, an are real numbers, and n is an element of the natural numbers union with 0. Polynomials form a vector space. Why? Think through it. Sum of polynomials. Take two polynomials, add them together. Do you still have another polynomial? What's a polynomial? It's a sum of finitely many power functions, right? So if you think about it, the sum of two of these is again another of the same type. And scalar multiplication, we just multiply as we usually do. So this is also a vector space over the reals. Yep.
Can you have a vector space that just has 0 in it?
Sure. That is example 0, now that you mention it. And you can pick any field you like. If that's the 0 in the field. And yeah, so it's the trivial vector space. But yeah, that's a vector space. It will almost, well, it will either, no, 0 plus 0 is 0. So many of these things are sort of trivially, sorry, pun intended, satisfied. 0 is minus 0. 1 times 0 is 0. There's lots of oddity about this example, but yeah. All right. Of course, you could take this and replace it with what? Complex. Z mod 3, right? Any of your favorite finite fields? Can you think of any other ways to mix and match examples I've already given? How about this? I'm going to stop here. I could keep going, but I'll stop here. How about this? How about V is equal to things like this? F of x, g of x, h of x, I of x, such that f of x, g of x, h of x, I of x are in the polynomials over x. 2 by 2 matrices of polynomials, also a vector space. If I add two of these things together using usual matrix addition, it's again a 2 by 2 matrix of polynomials. If I take a scalar multiple by a real number, again, I get a 2 by 2 matrix of real polynomials. All right, I hope I've by now convinced you that this definition is stupidly general, right? So as a rule of thumb, if you have things and you can add them together and you get another one of those things, and if you have a way of multiplying those things by some scalar, this is a vector space, right? And so you're like, well, why do you talk about vector spaces? Well, there's a simple reason. What this means then is anytime I can prove something, right? If I can prove something with absolute certainty about an arbitrary vector space, I have automatically proved it for all of these. See, that's the efficiency of abstraction. We have a definition which is suitably abstract, then if I prove things about vector spaces, I prove them not about one thing, but about all these things all at once. All right, so there's that. Now, right, there's really not much to say. I mean, we have to have these things out on the table because these are the things I don't really want you to prove. I want you to accept on faith because proving them is just, I mean, if I was to ask a test question about this stuff, basically I would just be like, for this point set, can you tell me how you would add vectors to give it a vector space structure? That would be the only question I could reasonably ask there, pretty much. And I probably wouldn't even ask that because it's not really that interesting of a question. The next thing, though, well, at this point in my notes, I have a few, and the notes I haven't shown you yet. Sorry about that. I'm working on it. Some of you asked me to put the next homework together, so I dropped everything and I did that first. So I'm sorry because I did that, and because I have yet not. I haven't quite learned how to not sleep yet. Once I master that, then I would be on top of things today, but not there yet. Working on it. But the next big topic is that of subspaces. the thing that goes between subspaces and what I'm saying right now is less interesting. There are a number of basic propositions you can prove just from the axioms are true for arbitrary vectors. So like, here's one of the things you can prove that's not an axiom. So here's a theorem that I will not prove in here. I may ask you to do these in the homework because those would be the stupidest kind of homeworks. Those would be homeworks where basically I'm asking you to read the notes and write down what I wrote in the notes again, which would be boring, but maybe the best way to present this material. 2, c times 0 is equal to 0. 3, these were not axioms, but these are true for arbitrary vector spaces. And 4, if c times x is equal to 0, then c is equal to 0 or x is equal to 0. Let's see here. This is for all. I should take a moment of our time to say these things to you, though. That is true. So this was, I can't tell you the number yet, but this is one of the theorems that'll be in the notes. So 0 times any vector is 0 vector. Any scalar multiple of the 0 vector is again the 0 vector. Minus 1 times any vector is minus the vector. This is the difference here is this is minus 1 in the field. This is the additive inverse of the vector. These are different things, all right? C times, if you have c times a vector is equal to 0, we get this like factoring kind of thing, right? Either c is 0 or x is 0. They could both be 0 too, of course, right? I mean, they're mathematical or. And we also get this law of cancellation. Oh, come on. You're like, well, how do you prove this theorem? You prove this theorem through like really, really careful step-by-step arguments from the axioms, all right? I've given you some homework, so I need to tell you something else in order for the homework to make sense. So I must move past this. All right. The other thing we have is a law of cancellation. So if a, x, and y are vectors in a vector space V, then if x plus a is equal to y plus a, that implies x is equal to y. So we have this law of cancellation. None of these things I wrote in purple should be especially surprising to you. All right? But what I want you to understand is that these can all be logically proven through systematic arguments based on the axioms. Right? Which is good. If some of these things weren't true, students would probably make mistakes, right? Because you would accidentally assume one of these things was true, and they wouldn't be true, and then you'd be in trouble. But they are. All right. Subspaces. What's a subspace? Actually, before I do that, I will just take a breath. Tell me what time it is before I take a breath. 12 what? 12:34. Yeah, okay. So are there any questions about this? Yeah. The squiggles? Oh, lemma. Lemon, yeah. Lemma. L-E-M-M-A. Lemma. No problem. Yep.
Can you have a vector space over the field of the complex?
Yeah, sure. We could have a vector space. Could the reals be a vector space over the complex? Huh. Huh. So you want to take V equals to R and C equals to the field. I think not, at least not with respect to anything I can immediately think of, because if I look at C times X, I would have CX, right? But if C is a complex number and X is a real number, almost certainly I'm going to have CX as generally a complex number, which would not again be an element of the vector space again, right? So it looks to me like scalar multiplication won't be closed. Unless you can think of some sort of non-standard way of multiplying complex numbers times real numbers to form a scalar multiplication. So not with respect to the usual operations. Interesting question. Yeah, it's a new question for me. All right, anyway, other questions? Tell you what, let me go on. Definition, a subspace. If V is a vector space over a field F, and if S is a, well, let's say if W is a subset of V, which is a vector space with respect to the operations of V restricted to W, then W is a subspace. Right? We denote W less than or equal to V. So this notation, when you see it, I'm not making some statement about inequalities. That is a notation which tells you that W is a subspace of V. All right? That should be distinguished from what? There's a difference. This one is curvy, right? That one's jagged. The curvy one, what's this say? Subset. Subspace. Subspace is more structure. You can have subsets which are not subspaces. Again, a subspace of a vector space is a subset which is once more a vector space in its own right. Es bueno? Now, you might be like, wait a minute, so if at this point, if you've read the homework, you should be like, oh, that's awful. You've asked me to check 10 axioms for these weird subsets of given vector spaces, right? Because like most of your homework is of the form, here's a set, which is inside some other vector space. Prove or disprove that this is a subspace, right? And if the definition were all that there was, that would be a bad place to be. But thankfully, there's two major theorems about subspaces which are useful to us. All right, so here's the two big ideas. The one theorem we have is that if W is a subset of a vector space V, and if W is not empty, set such that two things hold, such that one, x plus y, excuse me, let me say it again. If x and y are elements of W, that implies x plus y is an element of W. And two, if C is in the field and x is in W, that implies that Cx is in W. I'm sorry, I seem to have neglected an important detail here, which was what? So I'm talking about V over the field F, okay? This is being done with respect to the field F. Then what? What's the punchline? Then W is a subspace of V. Bam. This theorem doesn't seem to be clearly stated in Curtis, unfortunately. And I can respect that. I mean, this theorem is like logically equivalent to many things he says in the chapters, the sections I've asked you guys to read. So, okay, I mean, whatever. But I will have this as a standalone theorem in my notes. I refer to this as the two-step subspace test. Two-step subspace test. You can make it into a one-step if you do a slightly more complicated move. Okay, but all right, that's the one amazing tool we have to prove something's a subspace. There's an even easier theorem, and that's that if you let if the span of S, right, is equal to the sum I equals 1 to k of C sub I, let's say S sub I, such that Ci is in the field and Si is an element of S and k is a natural number. In other words, the span of S is the set of all possible finite linear combinations of vectors in the generating set S, where the scalars for the linear combinations are being taken from the field. Some people might put a sub f right here, just to indicate this is a span over the field. Almost generically speaking, the spans I've written for you are real spans. Okay? I think that's at least true in the homework I gave you guys. All right, so if this is the case, and if S is a subset of a vector space V over F, then what? Check this out. Span of S is a subspace of V. It's almost too good to be true. So you mean to tell me, if I'm looking at a subset of a vector space and I can identify that it's a span, sorry, game over, I'm done, it's a subspace. Yes, I do mean to say that. Let me see here. We should look at the proof at least of the two-step test in here. Before I do that, I probably should show you guys an example. So the reason I gave you guys that list of examples in part is so that you already have a context. You say like, oh, these spaces are vector spaces. Oops. Where was I? Again, don't mind the numbering here. I will be fixing it. I'm sorry. Try as I may, I always get behind. I said, oh. Come on. All right, well, that'll work. So here's again, the numbering will change. But this is the theorem. This is the two-step subspace test. You got a subset of a vector space, W non-empty, W is a subspace of V if and only if the following two conditions are true. Now, of course, I'm not keeping it real this year. Sorry, true. But last year, I think my students like me more because I kept it real. But sorry, I have higher aspirations for you guys. So W is a subset space of V. That means it's a vector space with respect to the operations of addition and scalar multiplication. Thus, 1 and 2 hold true. Fine. In other words, this is an if and only if. All right. So I say it as an if then, but it's also the other way it goes around. Clearly, it's closed under addition and scalar multiplication if it is a vector space with respect to the restriction of the additions. Okay, here's the interesting direction. It's actually not that interesting. Suppose W is non-empty set, which is closed under addition and scalar multiplication of V. We want to prove that W is a vector space with respect to the operations inherited in V. All right. Pick 3 vectors in W. Then if they're in W, and W is a subset of V, that means that they're also in V. So we can use axioms 1 and 2 for the vector space, which we were given to begin with. And we get that x plus y is equal to y plus x, and we get that x plus y plus z is equal to x plus y plus z. It's like, it's automatic. Okay, maybe this is why Curtis doesn't bother writing it. I don't know. So we get axioms 1 and 2 for W by theft from axioms 1 and 2 for the ambient vector space. And the rest of them are just the same argument. It's just the same thing over and over and again. If you have a vector in W, it's also a vector in V. So You know, if I have that the addition is closed, then, well, anyway. Yeah. Let me look at a proof of the span, which is a little bit more explicit. Let me put it this way. Actually, I will prove the span thing carefully, hopefully next time. That's part of a larger discussion about linear dependence. What you guys probably need to see from me at the moment is an explicit example or two. And sometimes a non-example is as important as an example. So here's one. I'll give it graphically. What if you look at this set? So let's say W is x comma y in R2 such that x and y are both greater than 0. It's definitely a subset. It's definitely non-empty. And you know what? It's even closed under addition. Check that out. It is closed under addition. If I take two vectors in here, like this one and that one, right? Then if this is y and this is x plus y. So this set, it's even closed under addition, right? Oh, but scalar multiplication is a problem, right? Because this is minus x, right? Which is not an element of W. So, therefore, W is not a subspace of R2. Oh, yes, I did. Can you guys, I mean, you are the weakest link. Goodbye. We only need to find one. But are there other complaints you could make, complaints you could lodge against W in terms of its status as a vector space? How about this? 0 is not an element of W. That's kind of a big problem. That's a pretty good place to start when you're thinking about something being a subspace. If it doesn't have 0 in it, the 0, whatever that 0 might be, 0 function, 0, 2 vector, whatever, game over. Let's look at a more positive example. Let's look at the vector space of 2 by 2, and I'll keep it real, real matrices, although that's just for, okay. And then we could let W be, let's see here, how about A, B, B, A, like that, such that A and B are real numbers. You can ask, is W a subspace? Well, it's clearly non-empty, right? So observe 0, 0, 0, 0 is an element of W, right? So therefore, W is non-empty. What if I take two things in W? What if I say take A1, B1, B1, A1, plus A2, B2, B2, A2, right? What do you get? So assuming that we're using the usual addition of matrices, which is assumed here, right? A1 plus A2, A1 plus A2, right? B1 plus B1 plus B2, and B1 plus B2, right? So what do you get then? Is this something in W? Does it pass the test? Think of W as a party. Think of the condition as a bouncer. Does it make it in? I don't know, this isn't really part of my life experience, but it seems like it's fun to talk about. But, so yes, this is again an element of W, right? What if you took a scalar multiple? You got CA1, CB1, CB1, CA1. Is this an element of W? Yes. So therefore, this set is closed under addition, and it's closed under scalar multiplication. Therefore, by the two-step, it's also non-empty, because I showed zeros in there. It's therefore non-empty, and it's a subspace of R2. It's a vector space in its own right. Two more examples, then I'll let you go. Sorry, I'm late. How about this span of 1, 2, 3, 1, 1, 1? Right? This is a subspace of R3. Lorenzo could justifiably argue, no, you meant it's a subspace of C3. And I could say, yes, that's true. That is an ambiguity in my current notation. So for those of you who are bothered by that ambiguity, we could put a sub R there to be clear. But that is in fact also a subspace. I'll prove that for you next time, that a span is in fact a subspace. The proof is pretty much just that the sum of linear combinations is once more a linear combination, and if you take the scalar multiplication of a linear combination, it's again a linear combination. So by the two-step test, a span is a subspace. My last example for you guys today is a little bit more general. If I take V to be the set of, say, n by n matrices over a field, I can look at W, say, the set of symmetric matrices. I can say A in Fn by n, such that A transpose is equal to A. And we can prove that this is a subspace. It's actually easier to do this than my previous example. So let's see here. So first of all, 0 transpose is equal to 0, right? So therefore, 0 is an element of W. So W is not empty. And if I let A and B be an element of W, and if I let C be a scalar, observe, if I have C times A plus B transpose, what do I get? By properties of transpose, right? But what is that? Why do I know it's CA plus B? Right, because A transpose is equal to A and B transpose is equal to B, since A and B are in W, right? The key point here is that A and B are in W. And those conditions are what make vectors in W and W. And then, what do you have? Well, you've got this is equal to that, right? Which shows you that C plus AB, CA plus B is an element of W for all C in the field and A and B in W. And then, of course, what can you do? You can take B equals to 0. That gets you part 2. If you take C equals to 1, you get condition 1 in the two-step theorem, right? So if I can prove this, I automatically get both of the steps at once. This is the one-step test I was talking about. If you can prove it for an arbitrary scalar plus a thing, you automatically get both, right? You just take C equals to 1 or take B equals to 0. So I should have the solution posted shortly. Savannah? Joseph D. Cooper, Matthew Russell, Alex Vogel, Adam. Yeah. Oh yeah, hit the red button again.